All right, so we have two quizzes this week. One is on Wednesday, one is on Friday. And so the pretty important topics will be covered this week. So today we'll talk about the voltage multipliers, charge pumps, sample and hold circuit, which is really classic and popular circuit being used for so many different things. And then we'll analyze ADC's parameters, including DNL and NL. And there will be a homework assignment due March 13th, which is a Friday right before the spring break. Okay, and the two quizzes on Wednesday. The Wednesday quiz is about voltage multipliers, and the other one is charge pumps. These are pretty important because both circuits are being used for the sample and hold circuit. So it's important to understand both. Okay, so now let's come back to this schematic and let's see what's really going on for that circuit. I drew a little a diode and capacitor circuit last week, and I told you some incorrect information here. So for a circuit like this, if you have a sine wave swing around zero, okay, and the output won't be positive bumps like this. And the reason for that is whenever this one is being forward biased, it's dumping charges to this cap. But whenever the voltage, after it reaches the peak and starts going down, the charges have nowhere to go because already after it charges up, this VL, the voltage reaches the maximum over here. Okay, in order to reduce the voltage, it has to discharge the cap. But the thing is, this one has a bar here, so the charges has nowhere to go. So it turns out that the capacitor is going to hold the charge forever if you don't discharge it. Eventually, this one, you can also say this cap is here performing as a low-pass filter. So eventually, all these bumps are getting filtered out. But eventually, it's just a DC voltage being held at the two terminals of the cap. However, you probably have seen some outputs like this, and that is from a circuit only has a diode and a resistor like this. If you have an input swing around zero, and now your output looks like this. Let's take a look at this circuit and see if that makes sense. Why this input will give you this output? So resistor here will be totally different from a capacitor at the output. This one allows charges to flow, okay? So eventually your negative voltage won't be able to go back, okay? But it's just holding, so there won't be any current, so it's going to be 0 volts. No current across the resistor, and there won't be any voltage drop. So eventually you are getting 0 volts over here. Okay, that is why, and this is also called a half-wave rectifier. Okay, so the important circuit structure comes when we swap the position of the capacitor and the diode. You'll see something like this. Let's say I'm having 0.5 volts, it's negative voltage. So negative 0.5 volts, which means here is higher potential, here's lower potential. So what's going to happen is it's going to charge up the caps through the diode this way, and eventually giving you plus minus from right to left 0.5 volts. Right? And whenever this reaches here, because it's a square wave, this becomes 0.5 volts, but positive version of it. Become plus minus 0.5 volts. Okay, since you always ground this point, keep in mind the ground point is very important. You have to find out where's the ground. So which means when you are probing, when you are looking at the voltage at the output, all the voltages are relative, right? But when I'm talking about the voltage at a certain node, I mean the voltage from here compared to ground, okay? So you have to know where's the ground first in order to look at the voltage output. So this is always ground. And if you have ground which is 0 volts, it's being boosted by 0.5 volts by the power supply. So here it becomes 0.5 volts. It's being boosted by this capacitor one more time. Eventually you are getting 1 volt for the output. Okay, so after that 1 volt, this one becomes, because this is the input, right? It's going to oscillate from 0.5 volts to negative 0.5 volts. Because this charge is not going to anywhere, still holding at 0.5 volts, but this one becomes plus minus from bottom to top 0.5 volts or negative 0.5 volts. So you can see these two voltages are getting cancelled out. So you have 0 volts here being decreased by 0.5 volts, you are getting negative 0.5 volts here. And then being boosted by 0.5 volts, eventually this becomes 0. So your output will be boosted by 0.5 volts. It's like being lifted. And that is why you are having this, okay, eventually, from 0 to 1 volt, okay? So think about the circuit we just introduced from page 1, from this one. So this is still not quite useful if you really need a DC high voltage output. So we need another circuit after this. We need this little filter here. This is still ground. Because this point, the voltage here is, keep in mind the quiz is probably going to ask you to draw the waveforms, voltage waveforms from this node, from this node, from this node. So this one becomes this, it's being lifted. And this is exactly the output from this circuit. After it's getting charged up to here, it won't change anymore. Even though it's not a sine wave, not the bumps like this. It's very similar, okay, very similar. So what's going to happen for the output here is it's going to become a DC voltage. So it's going to charge up here and then maintain as that 1 volt. It's very close to 1 volt if we ignore the drop here, right? Ignore it. So it'll be pretty much 1 volt DC power supply. So you can use a circuit like this to build, to output a high voltage DC voltage. So it's just the one stage. If you keep adding more stages from this point, okay, you will be able to generate up to like a few thousand volts. Okay, but that's pretty much analog circuits we'll cover in that class. So we don't really care about high voltages. Usually it's 20 volts as a maximum. This 20 volts could be quite useful. You know, sometimes for the memory circuits, the flash, right, your USB, all the flash memory cells, they are using somewhere around 20 volts to trap the charges to the gates in order to memorize a certain state. Okay, that's how that works usually. But other than that, it could be just a little bit above your VDD in order to do your sample and hold. Let's talk about that really quick. So we'll introduce a sample and hold circuit from the charge pump. Very similar circuit. Okay, input, capacitor, VDD, and this one's, it's all digital circuit, so we are assuming it's from 0 to VDD. Digital circuit. So my question for you guys is, what is the voltage at the output? You have to have that kind of model in your mind, how capacitor works for digital circuits. How capacitor works. So first, my question is, you have a DC voltage here, like this, 5 volts, and it's been connected like this for 100 years. Is there any current in the circuit? Any current in the circuit? Why? The DC circuit is getting disconnected by the capacitor, right? So our pulses DC circuit, DC voltage, depending on where you are looking at, right? If you're looking at this area, they are DC voltage. So it's given that DC voltage is not giving any current to the capacitor. However, are you going to have any current flowing back and forth in the capacitor if you give a series of pulses as the input instead of 5 volts? But it's a 5 volts pulse, turning on and off. Are there going to be any current? Yes. Right? Because turning on and off is charging and discharging the cap. So during this ramp, there will be current flowing in or out. Discharging is going to be out. Charging will be in. So it's current flowing back and forth. And you're saying, hey, it's disconnected. How do I know you have current on the other side? How that works? Let me show you one very simple simulation over here. Are you comfortable with a capacitor circuit? With the power supplies and all these AC signals? DC offset 0, amplitude 1 volt, frequency 1K. Just create a really simple sine wave. This one. Wire. This is 1U. Wait. Back. 1U. Micro. Oh, I got 2 for some reason. What happened? Get rid of it. Okay. Right. Now I'll do a simulation because the sine wave is 1 kHz, so probably I'm gonna run, let's say 10 milliseconds. 10 milliseconds, so I can have 10 periods over there to look at the waveforms. All right, so this is a sine wave, right? No doubt. So I gave a sine wave to the input. Okay, what about the output? For this circuit. What the output would be? The same?
Maybe 0. Cancels out.
0, you ground it, you got 0, right? Is it grounded? Is it grounded? It's not, right? You didn't ground it. And you don't even have a resistor to limit the current. What does that mean? If you have a resistor, there will be a time delay. There will be a phase shift. If there's no resistor, it's just a pure conductor, okay? And the capacitor is going to pass AC signal. And you're thinking, hey, I got an AC swing here on one side. How could that happen? This side can have the same AC signal. How could that work? Same, even no phase shift. If you add a resistor, there will be a phase shift. Now we can do the calculation. This is from circuit 1. But there won't even have any phase shift. It's just exactly the same amplitude, same phase. So the way that works is whenever it's charging up over, it's pushing charges over here. It's expelling charges, same amount of charges to this terminal as well. Okay, that's why it's getting current flowing through the capacitor. It's actually not going through the cap. It just looks like it's going through the cap. You know, it just the charge is going in and out to the plate of the capacitor. Okay, and now look at this one. Okay, square wave looks different from sine wave because it's not always changing. It's getting stabilized at a certain point. But if you oscillate this fast enough, it performs really similar in a similar way as a sine wave. But that's not something we want to worry about. Okay, it's just like if there's any current flowing in or out from the cap or not. However, we only look at this point. It charges up the cap, then it stops. And when it's pulling down, it discharges it. That's something we need to know. Okay? Keep in mind, in the future, if you go to graduate school or if you go to a company, working for a company on some nonlinear circuits with capacitors in there, you need to know that whenever you are charging up on one terminal, it's passing the same instantaneous signal is passing through the cap to the other side. Okay, and when it's pulling down to ground, it's pulling charges out from the cap. It's doing the same thing to the other side because this ramp here is AC signal. The ramp. Okay, this is not AC, but this is the AC. Okay, it's changing. Whenever it changes, remember the equation for capacitors current is IC equals what? CD VDT. Okay, as long as there's a capacitance, yes, definitely there's a capacitance, and as long as there's a delta V, if V is changing, there will be a current. There's the current. If there's a V is changing over time, there will be a current. Keep in mind. Are these voltage changing over time? Yes, it's a ramp. This is time domain. Okay, so there will be a current. So it's going to charging and discharging the cap. So now let's look at it. So whenever I'm pulling, if I'm pulling from here, using this folding edge, pulling charges, like doing this, what's going to happen? Like doing this. If it's pulling, what's going to happen? Are you forming a circuit? This is grounded. Are you forming a circuit? Yes, because VDD is a power supply. Okay? Ground. They're grounded. So this is forming a circuit. When it's pulling, it's actually dumping charges to the cap from the VDD. It's doing this. Very important, okay? You should know that. Whenever a source is pulling from the other side of the capacitor, okay? And this side, which connected to VDD, will dump charges to the cap. Okay? Until what? Until VDD. So this one becomes VDD. There will be a little drop across it. Let's ignore it for now. Usually it's like 0.6 volts. We don't have to worry about that for now. Okay? So it's going to dump charges to the cap until VDD. Okay? And when it goes up, what's going to happen? So this is from VDD to 0, right? And this becomes 0 to VDD. Okay? So which means the charges dumped from the VDD previous from VDD will stored at the cap and has nowhere to go. And will stay there. And then after this cycle, it goes up to VDD again. And you're having a plus minus VDD here. If you look at this circuit, it's basically two batteries in series. You're having one VDD, two VDDs. So what's the voltage here? what's the output here would be the maximum? 2 VDDs, right? It's gonna be 2 VDDs. That's why it's called a charge pump. It's pumping up. So what if after VDD, this becomes 2 VDD, and then this goes down to ground again? Guys, so this goes to ground again. What's gonna happen? This one becomes, so this voltage here, if this goes to ground, which means the voltage here becomes 0 volts, right? 0 volts. And you are grounding here. If it's 0 volts, there's no voltage drop. 0 volts here, 0 volts here. So it's totally 0 volts, right? And there is only one VDD here. Only one VDD. So this point is gonna swing around 2 VDD and VDD. Swing between VDD and 2 VDD. Okay? Any question on this? So let's keep going, adding more circuits to it. Let's see if that makes more sense. We know that this is a little charge pump. And we are getting VDD to 2 VDD here. And if we're adding a diode and a capacitor, there's a little filter here. So this one will give you a DC voltage, right? And what is that DC voltage? Remember we drew that circuit, page 1, right? So this one, and eventually it becomes a DC voltage at the peak voltage, at amplitude. Same thing here. This one swing between VDD to 2 VDD. So this one will give you a DC voltage around 2 VDD. It's getting filtered out. Okay, it's a 2 VDD output over here. All right. And we have learned that NMOSes are good at passing zeros. Okay, so in that case, if we have an NMOS like this, VDD here, and this one's have a rising edge from 0 volts to VDD. Okay, so what you're expecting as this node, like a passing gate. If it's trying to pass VDD to this point, are you able to pass the entire VDD to this point? So whenever this is trying to turn on the gate for the NMOS, it's a digital circuit, okay? It was 0, and now it's trying to turn it on. So this rising edge going up to VDD. So during the way to VDD at this moment, and the NMOS will be off at here. The reason for that is, if we're assuming this is able to pass VDD, then eventually your VDD minus VDD is going to be 0, right? So VGS becomes 0. It won't happen, okay? So it's going to stop at which point? So what's the maximum voltage you can have over here at the source? It's going to be VDD minus VTHN. Why? Because whenever this one goes up to VDD minus VTHN, wait, is that right? Oh, yes. So whenever this one's over here, it's still able to pass VDD minus 2 VTHN, but whenever this keeps going up, no more can be passed through it because it was off during this period. Okay, so only because this is the input, you can control it, so you can always pull it up to VDD. But the thing is, after this voltage, it won't keep going up. So it's like, stop, okay? It won't go to VDD. Does that make sense? So that is why NMOS is not good at passing ones, but it's good at passing zeros. Passing zero is fine. So for example, you just want to pass zero over here. You have a VDD, you got 2 zeros, it's going to work, no problem, because VDD minus 0 is going to be VDD as a VGS, which is way larger than the threshold voltage. So what I want to tell you from this model is, you want to keep this in mind as a conclusion, okay? So whenever you are pulling down charges from the NMOS, let me show this. If I replace the diode on the top with the transistor, okay, like this. And most transistors are way easier to fabricate than the diodes, right? So because most of the circuits are CMOS transistors, we just can add another CMOS transistor and do a gate drain connection, then I can form a device which performs very similar as the diode. So usually we use this kind of connection for a transistor as a diode in the circuit. Okay, so if you do this, what is the maximum voltage you can get at this point? When it's pulling, when it's pulling. That's VDD here. So after today's lecture, if you can understand this one as a takeaway, I'll be really happy. You know, even though it's really simple, but still, sort of like a model in your mind, have to form your mind. So when this is pulling, keep in mind, it's dumping charges to the cap. Okay? If you don't understand why, I'm telling you it's gonna happen, okay? Like what I said in page 2, okay? So it's gonna happen. So it's gonna pulling charges down. It's like grounding it, but only happening at the ramp. Only happening here. Whenever it reaches the DC voltage, steady state, the DC voltage is not changing anymore. However, during the ramp, whenever it's pulling, it's an AC signal, it's gonna pass through that capacitor, it's gonna dump charges to the cap, all right? So when it's dumping charges to the cap, ideally, the final voltage across the cap will be VDD, because it's trying to dump all the charges, or eventually form a voltage across the capacitor to be the same as VDD, because this point is grounded. And whenever the voltage here becomes 0 volts, and there's no difference, okay? There's no difference. So which means here will be 0 volts as well, so it's dumping VDD to this cap, okay? Ground on the other side, and eventually it's gonna form a VDD over here. Ideally. However, what is the real voltage would be at this point? Because the NMOS is not good at passing ones. Okay? So you are not able to get entire VDD to this point. And the maximum voltage you can reach, so this point can reach, is going to be VDD minus VTHN. Why? Because this is the gate drain shorted, so the voltage here is also VDD as a constant. Okay? Whenever this point reaches VDD minus VTHN, what is the VGS? No, this is always VDD, right? The gate is always VDD. And whenever this one, so whenever you turn it on, this one start dumping charges to it. Okay, where you are pulling on this terminal, it's gonna dump charges. So the voltage here starts rising. All right. Whenever this voltage rise to VDD minus VTHN, VGS becomes what? What is VG? What is I? VS. So yeah, what is VGS though? All right, so VGS has to be larger than VTHN in order to keep the NMOS on, right? But after this point, if this keep going up, it's going to turn off the NMOS. So that's why it won't keep charging up this terminal anymore. So eventually, this one will be VDD minus VTHN as a maximum voltage, which is also the voltage across the capacitor, the two plates. And now it starts going up. It's going to charge up. And then it's going to form a VDD over here. Why is VDD? Because it's always digital signal, like 5 volts logic. So it's going to add another VDD over here. And that VDD, because this point is always grounded, okay? So in that case, what is the voltage over here as the maximum?
So there's another VDD like input on that left side.
Yeah. This is digital signal, right? It's VDD 0, VDD 0, like that. So whenever it's 0 at the floating edge, at the ramp, it's pulling, right? It's pulling. So it's discharging from the voltage source and it's dumping charges to this point, right? And then eventually form a VDD minus VTHN voltage across the capacitor whenever at the floating edge, And after the floating edge, it maintains a 0, which is not doing anything because the DC voltage is not changing. There's no current. Okay, and then right after that 0 volts, it starts rising again. Okay, and this, because this is the diode, it's a diode connection. The charge is not going to anywhere. It's very similar to the diode. Charge is not going to anywhere. Why is the charge is not going backwards for this connection? Why? Why is it only going from here to from top to bottom, not bottom to top? Because VGS is what? If you are treating this as this is the S, right? If this is S. So VGS is what? VGS is 0 because VG, and VS are shorted. So there's no VGS. Okay, so 0 VGS. There's no way you can flow current from bottom to top. That's why it's called a diode connection. You can do a diode connection for your NMOS because of that. However, there is a VGS difference which is able to turn it on. So this allows current flowing down. That's why you are able to charge up this cap. Okay, anyway. So after the 0 voltage, it goes up, but the charges has nowhere to go because it's a diode connection. It's not going up. So eventually this goes up to VDD, and then you got another VDD add to the previous VDD minus VTHN. So what's the voltage at the output eventually as the maximum? So it's basically adding another VDD to this value, right? So it becomes 2 VDD minus VTHN. Okay, so the ultimate goal for this lecture is whenever you see a circuit like this, you should know that the output voltage swings between VDD minus VTHN to 2 VDD minus VTHN. That's the conclusion here. No, because after that it goes down to 0 again. Goes down to 0 again. So it becomes this, right? It becomes plus minus. No, it becomes 0. Becomes 0 volts. Because it's from V to 0. If this is 0 volts, and whenever you are talking about the voltage node, you are comparing to 0 compared to ground. So this stays at VDD, right? It's like a battery. Okay. From this circuit, we can build a bigger charge pump. Let's draw this circuit first, VDD. Let's look at this one first. Like I said, this is a diode connection. This thing is the same as this. Okay, it does the same thing. So this is like the filter circuit we drew at the very beginning of the class. And this one is the charge pump we just introduced over here. So the voltage at this point is going to swing from here to here, right? It's going to be like this. VDD minus VTHN, and 2 VDD minus VTHN. However, after the filter, this is going to stabilize the voltage. After it's charging up, it's going to form a DC voltage. So my question is, ideally, it's going to pass through everything, but however, it's an NMOS. So eventually, this DC voltage, there will be a loss. It won't be the peak voltage over here, right? So what is that voltage, DC voltage at this point? You are thinking, hey, it's gonna will be stabilized at this point to form a DC voltage. Ideally, yes. However, it won't. So what is the loss across this NMOS? Similar to the one over here. I hope you can answer this question. So from here to here, what is the loss? How much did you lose? Did you get the full VDD? No. You lost the threshold voltage. Okay? So it's going to be the same thing here. Even though you got a 2 VDD, but you are losing 1 threshold voltage at this point. Because of the charge pump, you are getting 1 more VDD. However, because of the NMOS, you are losing 1 threshold voltage. So that's why this one becomes 2 VDD minus VTHN. Okay? And then it's going to pass another NMOS. So what is the voltage? What is the DC voltage over here? If you are looking at the peak voltage. Okay? And because the property of the circuit is not going back, it's eventually just staying at the peak voltage. But there will be a loss, right? And that loss, every time you pass through that NMOS transistor, you are losing 1 VTHN. Okay? So very similar here. Since we know the peak voltage you are getting here is 2 VD minus VTHN. So after passing that NMOS, you are losing another VTHN. So eventually the voltage here becomes what? So 2 VTHNs, right? So even though you got 2 VDDs, but also you are losing 2 VTHNs. Okay, I explained this to you guys if you couldn't eventually get it, but at least you should have this kind of model in your mind in the future. Very important. If you have a circuit like this, whenever it's pulling, it's going to pull charges this way at the edges. Okay, same thing when it's bumping. It's going to increase the voltage over here as adding the voltage to this capacitor's voltage and forming a higher voltage. And that's the takeaways from this lecture. Okay, at least you can memorize it. Okay, we can boost the voltage further. So all these circuits are from the textbook. Okay. And we can boost it further by using a charge pump that's called Dixon's charge pump. Someone's name is Dixon, who invented. Okay. Here must be VDD. It's a digital circuit, so clock is swinging around from 0 to VDD, right? For sure. This is 0 to VDD, clock. And it's a clock bar, so there's an inverter in between them. So you can get clock inverted. I will spend the rest of the time to find out the voltage at each node of the circuit. Let's go Dixon's. So what's the voltage here first? Charge and discharging, right? So when it's pulling, what's gonna happen? When it's pulling, what's gonna happen? Boom, charges flowing down. It's like a waterfall, right? Pulling. When it's pulling, you're getting what? VDD minus VTHN. Okay? And then charge up. It's a diode connection, so charges don't have anywhere to go. Eventually, it's stuck. But however, since you are adding another VDD over here, from here to ground, there's a ground. Okay? It's adding from VDD to ground. So the voltage here becomes, I just label it, okay? A for A is from VDD minus VTHN to what? It's adding another VDD. So there will be a square wave swing between VDD minus VTHN and V2 VDD minus VTHN. Just boom, 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 boom like this. Okay, and then look at this circuit. Whenever this one is charging, let's say whenever this one is getting into VDD minus VTHN, which means this is pulling, right? This is pulling. If this is pulling, this one is pushing. It's getting inverted. So if clock's pulling, clock bar is pushing. You agree with that? So they are getting inverted. So the question here is, because there's no gate or no control across these NMOS. Okay? So in that case, the voltage here will pass through this NMOS and having a loss as which is 1 VTHN loss across the NMOS. So B is getting what? What is this pushing doing to this point? Let's use superposition, okay? Let's use superposition. Don't worry about this source for now. Don't worry about this for now. Just let this voltage from A pass through to B. Okay? So in that case, you are definitely minus 1 more VTHN, so you are getting 2 VTHN being subtracted. Okay? However, this is adding another VDD to it. This is adding another VDD to it, because whenever this is pushing, it's forming another VDD. Okay? It's adding another VDD to it. So in that case, you should add another VDD to each state. Superposition, right?
Where did the second VDD come from?
Over here, the clock.
Oh, okay.
Yeah. From this cap. It's doing the same thing, okay? So when it's pulling, it's charging up the cap by these voltages. So like pulling the charges across this diode. And what you can get here is similar to what you had over here for the VDD. However, it's just whenever it's pulling, it's just Let's see. So whenever this is pulling, this is pushing, right? Okay. So when this is pushing, you are getting 2 VDD minus VTHN. And when this is pulling, it's pulling all the 2 VDD minus VTHN to this point. But it's losing another VTHN. So eventually you are getting 2 VDD minus 2 VTHN, which is over here. All right. And during the other cycle, this is getting blocked because eventually this voltage is less than the voltage here. So it's not going backwards because the VGS is 0. Okay, so then another VDD across it, eventually are getting 3 VDD minus 2 VTHN. Let's do it one more time. Is that confusing? I know I'm losing 80% of the guys, right? 100%, let's say. Okay, did you get the point that whenever it's pulling, whenever here is pulling, this one dump charges to it and giving you a VDD minus VTHN? Is everybody getting that point? Okay, it's gonna be on the quiz on Wednesday or Thursday, Friday. I forgot which one, but it's important. Okay, so whenever it's pulling on one side, it's dumping charges to the cap and forming a VDD minus VTHN. All right, and then when this one goes up to VDD, it's adding another VDD to it. It's forming VDD plus VDD minus VTHN. So you're getting 2 VDD minus VTHN at this point.
So that VDD on the left is just clock.
Yeah.
Okay.
Good question. So it's gonna be VDD plus VDD minus VTHN. Okay, forming a 2 VDD plus 2 VDD minus VTHN. So that's how your voltage getting boosted. One more question here for you guys. Because the NMOSes are being shorted to the same power supply a lot of times, so the power supply for this guy is VDD, and I don't want to pass the entire VDD to the source. Okay, this charge pump is going to create a higher voltage than VDD, which is the highest I can get usually if I don't use a charge pump, if I don't boost it. However, since I'm using a charge pump, I'm boosting the voltage. Eventually, for example, VDD is 5 volts, okay? And VTHN is like 0.8 volts. So 2 VDD minus VTHN is giving you about 10 minus 0.8. It's about like 9.2 volts. It's way larger than 5 volts. And if I want to use this one as a gate voltage for a transistor like this, am I able to pass the entire VDD to this point? Trust me, this is the best part of the lecture. It's a conclusion. That's the whole point why we are doing this, right? Are we able to pass the entire VDD to the source if we have a higher VG? Yes. So if you are having VDD to be passed to VS, what's going to happen for VGS? Is this larger than VTHN, the threshold voltage? Of course. So it is still on. If I allow the voltage at this point rise to VDD, I'm still fine. So in that case, I'm able to pass the entire VDD to the source. I don't have that limit anymore. Okay, for the sample and whole circuit, at some point, you will need to pass the entire VDD to the source for some reason I'm going to explain on Wednesday. Because NMOS is not good at passing ones, but it's good at passing zeros, okay? So in that case, if I use a higher gate voltage, I will be able to pass both ones and zeros because this is shorted to ground, that's to VDD. So I don't have to worry about ones. But anyway, so it's always able to pass the entire VDD to the source. And that's the whole point of the circuit. And that's why we are trying to bump the voltage to something higher than VDD using a charge pump. But I have to understand why this happens, okay? Super important. I'm not losing the threshold voltage because I have a higher gate voltage. So I can form a higher VGS. and because you have to have VGS larger than VTHN to turn on the NMOS, and now I don't have the problem anymore because this is always larger than VTHN, even though I'm getting a VDD at the source. Okay, for here, if you ignore the rest of the circuit, just looking at this point, whenever this guy is pulling, it's pulling VDD minus VTHN to this point. Okay, and whenever this is pushing, it's adding another VDD to it. And whenever this is pushing, because the clock here is getting inverted, if this guy is pushing to this voltage, 2 VDD minus VTHN, this has to be pulling. So this is pulling the charges. This is pulling the charges across this NMOS, which is pulling this voltage through it. Like when you put VDD through the transistor previously, it's the same thing. Okay, you are pulling this charge or this voltage to this point. So eventually you are getting this 2 VDD minus VTHN. However, it's passing through another NMOS, is losing another VTHN. Eventually it becomes 2 VDD minus 2 VTHN minus another one. That's why you are getting this. Okay? And after that cycle, after this it was pulling, it start pushing. And when it's pushing, it's adding another VDD to this point. You used to have a VDD here, as adding used to have this voltage here, and now you're adding another VDD over here. Eventually you're getting one VDD added to this voltage, so you're getting 3 VDD minus 2 VTHN. And why it's not going back? Because the voltage here as the highest is only 2 VDD minus VTHN. And this is the diode connection. It's getting reverse bias. There's no current, no charge is going to go back. So it's getting trapped over here. So eventually it's swing between this and this. I will explain this further on Wednesday. Okay? No worries. It also took me a lot of time to understand every single detail about it. I will see you guys on Wednesday.